Okay, so today, where's the mic? We are continuing to plug through cost curves and firm production. It's going to be another kind of dreary one. I have to apologize. Less stories, less maps, more graphs. But this stuff is definitely on the midterm and the next problem set. So unfortunately, we're deep in the Econ 1 that you need to learn part. So apologize for a drier class, but here we go. We're going to be going through cost curves, looking at production. The computer's falling asleep. Maybe if I plugged it in, it wouldn't do that. I have the example in the book of a paper mill in Sweden, which is a little esoteric for us, but paper mills pollute. People want to regulate the amount of pollution from a paper mill. And somebody had good data on their costs underlying the Swedish paper mill. So that's our example we get to play with from the textbook. Let's see. So today we're going to talk about production and move that into cost curves. First I'm going to talk about emission standards. Last class we talked at the end of the class about emission standards. So we'll start out talking about emission standards. Then we'll do production curves, which are output versus inputs, and then we go cost versus output. So we move from just looking at inputs to outputs into cost for outputs, and then we'll go to Swedish paper mills. So strangely, I got out of the lecture the other day, and there was an announcement that President Obama was talking about emission standards on cars at the exact same time that I was giving a lecture on emissions on cars. I was like, wow, this is so relevant. So he was talking about trucks, big trucks. He went to a Safeway facility in Maryland, where they're working together with industry to design the super truck, he says in the speech. Trucks are 4%, big heavy trucks are 4% of the traffic on the road, but they're 20% of our carbon emissions. So like here's a place that we could target effort, reduce emissions from trucks, save gasoline, and save air quality, and reduce our carbon footprint together. And he actually used a couple terms that were very close to what I was talking about in motivating emission standards. Was set goals for what emission standards could be or should be, and then this idea of like let the automakers decide. Let the automakers figure out how to get there. We're not going to tell them what technology to use or how to mix gas and fuel injection in their engines. They're going to figure out how to get there. We're going to tell them what the goal is. So if you bear with me, I was thinking we should just watch a couple minutes of President Obama. So here he's giving the speech, and if you look at the timestamp, this is exactly when we were in class talking about the same thing. So it turns out that everything the president says is on YouTube or whitehouse.gov, so you can go find it and read through the statement. Let me see if I can. Hope this works. Oh, here's a question. Am I plugged into AirBears or not? That's something to do before class starts, huh? Let me connect to the internet. You guys going to see me type in my password? Sorry for not doing this before. We're in. Where's that president? All right, so I'm just going to play a couple minutes, and starting at minute 5 in his speech.
We're stuck in neutral. Even as other kinds of technology.
No, that's not really working, is it? I'll leave that on the page. Technical difficulties, bear with me. Thinking. So he talks about all the different things.
55 miles per gallon.
Pomp and circle. You got to hear that, the band playing. They must have to play that whenever the president shows up anyway.
Even as other kinds of technology left forward. And that left families and businesses in our economy vulnerable to fluctuations in oil prices. Every time oil prices shot up, the economy got hurt. Our automakers were in danger of being left in the dust by foreign automakers. Carbon pollution was going unchecked, which was having severe impacts on our weather. And that's why after taking office, my administration worked with automakers, auto workers, environmental advocates, and states across the country, and we set in motion the first ever national policy aimed at both increasing gas mileage and decreasing greenhouse gas pollution for all new cars and trucks sold in the United States.
That's what we were talking about.
And as our automakers retooled and prepared to start making the world's best cars again, we aimed to raise fuel economy standards to 35.5 miles per gallon for a new vehicle by 2016. Yeah, wow. That was an increase of more than 8 miles per gallon over what cars had averaged at the time. And what we were clear about was if you set a rule, if you set a clear goal, we would give our companies the certainty that they needed to innovate and outbuild the rest of the world. They could figure it out if they had a goal that they were trying to reach. And thanks to their ingenuity and hard work, we're going to meet that goal. 2 years later, we've already seen enormous progress. And we're building on that progress by setting an even more ambitious target. We're going to double the distance our cars and light trucks can go on a gallon of gas by 2025. We're going to double it. And that means, that's big news. Because what it means is, you got to fill up every 2 weeks instead of every week. And that saves the typical family more than $8,000 at the pump over time. I'm assuming you can use $8,000 that you're not paying at the gas station. And in the process, it cuts American oil consumption by 12 billion barrels. So we let the automakers decide how they were going to do it. We set the goal, we said, go figure it out. And they invested in innovative and cost-effective technologies. And some are already making cars that beat the target of nearly 55 miles per gallon. They've got plug-in hybrids, they've got electric vehicles. They're taking advantage of the investments that the Recovery Act made and American advances in battery technology, so cars are getting better, and they're getting more fuel efficient all the time. And for anybody who said this couldn't be done, or that it would hurt the American auto industry, the American auto industry sold more cars last year than any time since 2007. And since we stepped in to help our automakers retool,
Right, I'll pause it there, but what I wanted to just point out was he said this thing of like, we'll set the goal, we'll let the companies figure out how to get to the goal. That's the idea of how an emission standard is more efficient. Some people do it through hybrids, some people do it through clean diesel, some people do it through different ways. It's interesting how, like in this class, we're looking at a couple goals. We're looking at carbon reduction, reduction of other pollutants, but the president wraps the package into jobs for everybody, investments he's already made in clean tech, money in your pocket. So the president wraps the package in many different attributes, although we're just looking at a couple attributes here. So yeah, this was the emission standard. We let the automakers decide. All right, we are moving on to drawing some graphs. So we're thinking first, not about cost. We're thinking about how we have a production function that transforms inputs into outputs. So we have a production function, we have some inputs, and we get outputs. We're going to call this the total physical product. The physical product in terms of units of output that we get for units of input. And for right now, we're going to take all of the possible inputs and either compress them into one aggregate input or hold fixed the other inputs. So we're just looking at one x, okay? Because we need to graph things in 2 dimensions. We need our equations to be in 2. Once we do the total physical product, we will also look at the average physical product and the marginal physical product. The average physical product is this total product divided by the units of input, so averaged over all of the units of input that we put in so far. And the idea of marginal, we're always going to have to come back to the idea of marginal. That's where we are in economics. Everything is about marginal. Marginal is the additional unit Q out at the margin for an additional unit of input. At the point where we are producing, how many more units of output do we get for a unit of input? So we have a proposal for the way this is graphed. Here is our output up here, and our inputs are down here. One way that this is motivated is, so if we're doing Q equals f of x, a classic way in a classic econ 1 is that you would say quantity is a function of capital and labor. And our capital is our factory, and our labor is our number of workers. So for right now, capital is fixed. So this physical product is a function of how many workers we should hire. So just a function of labor. And this input down here would be workers, units of L, labor. So we think that it starts out, it gets steeper, more productive, then it hits a point and it sort of levels out. So this is our curve called total physical product. And there's a tool that we can use a lot of times first to figure out the average. And we can use array from the origin. And you'll see me do this a couple times. If we have a ray that goes to any point, this will have units of Q per units of X as the slope of this ray. Right? This is X, this is Q. Right? Rise over run, average, going to give us units of Q per units of X. Units of output per unit of input. So if we draw this line to any point. So one thing we can think about is the highest point this line is going to get is right about there. That's the highest as the ray is shifting up. So this point here would be the highest point that the average physical product gets to, that our inputs are yielding the greatest amount per unit at this point. And we can graph that. Then we have the marginal, which is sort of this instantaneous slope at any point. If it was calculus, we'd be the derivative, and we would be able to take these instantaneous points. In a discrete world, we take smaller and smaller chunks trying to figure out what the slope is at any given point. So the marginal, we have different ways to think that it's the slope, either instantaneous or in a discrete case. So we have a way to just think about these couple points. Let's do total physical product again, but this time it's flattened out. This is total physical product, and this is this quantities of output. Now, for marginal and average, we need to graph them on a different scale, which is a per unit scale, per unit of input. How much output are we getting per unit of input? There's a couple points to look at. So there's a point right here, which is called an inflection point. And when we have, sort of, if you know calculus or from graphing things, it's going from curving up to curving down here. So we have that inflection point. And then we have this point that we've already talked about, that if we drew our ray from the origin, this is the highest it would get to. Right? So that's going to have something to do with the average. And then there's one more point here that we have where total physical product actually starts going down. So if we think about this, we're adding workers. We have a factory. We're adding workers to our assembly line. At first, it's increasing a lot until we get to here. It's going up how much productivity they're giving us, how much units of output per worker we add. Then as we keep adding workers, they're getting less and less productive. Each additional worker is adding less and less until we get to the point of there's too many workers. They're bumping into each other. Our productivity is actually going down. So if we make these points go down into the space of the per unit, this one here is going to be the maximum of our marginal product curve. So the per unit employee that we're adding is going up till we hit this inflection point where each worker is producing more and more and more. And now each worker is producing less and less. They're producing some more, but less than the last worker that we hired. Okay? So that's going to give us the marginal physical product curve. And then this point here, I've already talked about this, is using the ray. This is the average, this is the rise over the run. This is the highest we got in Q over X. So that was the average. And it's going to actually cross here. So this is the average product per worker is going to be going up until this point. And then it's going to be going down after this point. So this is the average physical product. One more point that we had was this point where it started going down. This is a little bit academic, but we can think that there's places where if we hire too much input, it doesn't get any better. If we were adding nitrogen to our soil to grow corn or phosphorus, at first the nitrogen's giving a big boost. Then we get to some sweet spot, the nitrogen's giving us more corn, but less and less additional corn. After we put too much nitrogen on, it can actually burn the soil and burn the plants. We put too much fertilizer on, and things can't grow there. So if that's true, that point here, the marginal curve would cross 0 and become negative. If an additional unit is going to lead to less output, then the marginal is going to become negative at that point. So if total physical product starts to dive, the next worker actually made us have less than we had before, so the marginal product is negative. So yeah, just in terms of our marginals, mostly we want to think about there's a sector where we have an increasing marginal physical product, and then we have a decreasing marginal physical product for the second sector between the peak and this inflection point. One thing we can talk about is a law of diminishing returns to any given factor. So we think that in most cases, the marginal physical product will eventually be decreasing. So this implies that there's some optimum level. We can't just keep adding workers. We can't just keep adding nitrogen. There's going to be this law that's going to say at some point it's not going to be worth putting the extra units in. capital is fixed, the land that we're growing on is fixed, and so adding this variable input will at some point have diminishing returns. So a common way to say that would be that increasing input beyond some certain point is going to increase output less and less until at the top it's going to decrease output. So we have in our mind thinking like we're going to try to find the optimal amount of this input to put in, but at some point it's not going to be worth putting more of this input in. There's something constrained about it, the amount of land that we have, the size of the factory that we have. There's going to be some capacity built into our system that's going to not allow us to just keep adding indefinitely. There's another term which is marginal revenue product, which we can think of as the marginal product for that factor times the price of the output. So if we hire an additional worker and they can produce certain additional units of output, and we get revenue pricing our output at the price of output. So if we assume that the firm is a market-taking firm, they're going to be a price taker. They're just going to take whatever price they can sell their product for in the output market. So at the optimal level, the firm's going to take the marginal revenue product and equal that to the price of the input. If I'm going to keep hiring workers in my factory until the amount that that additional worker is yielding an additional output is equal to the revenue that I can get from selling that unit of additional output. If the marginal revenue product of the worker is greater than the cost of paying the worker, I'll hire more people. If the marginal revenue product of that worker is less than their wage rate, this should be less here, look at this, typo. So how much is this input giving me in terms of value from output? So this is the beginning. We're just thinking about quantity so far, and then we need to start thinking about costs. This is like, how much is the input yielding me? So now we need to move into thinking about costs. And we're going to say all resources are scarce. All inputs are going to have some opportunity cost or value to them. We either are buying them or it's something that we have that we're using up in a variable way or a fixed way. So there's always going to be a cost for the inputs that we're using. Maybe it's our time, maybe it's our workers' time, but there's always going to be an increasing cost as we increase inputs. So first we start with the cost function. That's a total cost for each unit of output. And then we're going to look at average cost at any point, which would be the total cost divided by how many units of output we have. And then we're going to do marginal cost. And we'll get into the formula for what marginal cost is, but we want to think about it intuitively before we write down some math and say it's the cost to produce that additional unit. The average cost is the cost to get here over how many we produced up here. The marginal cost is when we're up there, how much is that extra unit costing us at that point. So here we can relate what we already have. So here's our total physical product curve that we started with. And this is going to be quantity per units of input. So we're kind of flipping it when we do cost. This is going to be the costs of any given quantity. And here, we're going to have quantity. So it's sort of like we're inverting the shape because we're shifting what axis we're in. We're looking at the curve in a mirror or through a prism or something. The curves are going to be different. We think that the costs are going to rise, and then we'll get into some sort of sweet spot, and then they'll start going up really steeply. So this is the total cost curve. These are not matching up here. Let me do this better so that they match up. All right, so our inflection point is here, let's say, that we started with. And we have some sort of maximum point up here. So at the maximum point, costs are going to go up towards infinity. And this inflection point here is going to be where we're going to go from curving up to getting a little convex. So we'll say there's 3 parts to this cost curve. There's a concave part as we're increasing, then there's this little convex part. And then after that, total physical product just gets flat, and we're adding workers, we're paying for them, total physical product goes down, it's going straight up. But we just know that it keeps going up. So here we are adding workers. At first, workers are increasing our costs. And then we get to some sweet spot where we're getting more and more, we're moving to more and more units of output. We're not adding so many workers because they're like in this steep part here where each additional worker is producing a whole bunch more. And then at some point, the workers are producing less and less, and our costs keep going up. As we add workers, our costs are going up faster than we're getting more units of output at this point. So let's just look at our total cost curve. So what are our units? Our units are dollars. The costs per unit of output. We have a section where it goes up, a section where it's flatter, and then a section where it gets steep again. So this is a cost curve, and it has embedded some assumptions that we've seen. You know, we could say they're empirical regularities from seeing them in lots of firms. They say we're intuitive because they have some attributes of what we think happens in production. We would also, in some places, this would be variable costs, and we'll talk about fixed versus variable costs in a little bit. But we can also start thinking about our ray from the origin, and that's what that's going to get us in averages, right? And what's the slope going along here? Slope instantaneously at different points. All right, so let's try and put them, let's do the average and the total as we did before onto the same graph. So I need another bar here.